Hi students, welcome back on the presentation of wind energy. Today's topic is numericals on wind turbine, that is how to design a wind turbine. I am Professor Rakesh Unecha from Marathwada Mitra Mandal's College of Engineering. So let us begin. We will consider one problem. Here is the one. It is proposed to design a miniature windmill at a location where wind speed is 11 meter per second. What is the expected power output in watts for a wind turbine with 6-meter rotor diameter? Coefficient of power is 0.30. Generator efficiency is 0.80 and that of gearbox is 0.90. So the given things are diameter of rotor, that is capital D, 6 meter, coefficient of power Cp 0.3. What is coefficient of power? Generally, the turbine cannot extract all the power available in wind. So, the coefficient of power is the fraction of power available in wind that is extracted by the turbine. Generator efficiency 0.8, gearbox efficiency 0.9, and wind speed is given 11 meter per second. So, the formula is actual power extracted is 1 half rho into area into velocity cube into coefficient of power into efficiency of generator into efficiency of gearbox. Putting all the values, that is 1 by 2 into density. This density is the general density of air at 1 atmospheric pressure and temperature of 15 degrees Celsius. It is 1.226 kilogram per meter cube. If in numerical the density is not given, we generally take this density of air. This is area pi by 4 d square. This is velocity cube. This is Cp. This is efficiency of generator. This is efficiency of gearbox. After calculating, we will get 4983 watts, and converting into kilowatt, we get 4.983 kilowatts. Next problem. A 25 kilowatt wind turbine could produce actually only 50,000 kilowatt hour per year. Calculate the capacity factor of the system. First of all, what is capacity factor? Generally, turbines are designed for some output, but generally turbines can work only 65 to 80% of time in the year. So obviously the power actually produced by the turbine will be less than its theoretical power. So capacity factor is actual produced power divided by theoretical power. So given data is plant capacity, it is theoretical capacity 25 kilowatt, actual production is 50,000 kilowatt hour. So theoretically plant should produce 25 kilowatt these days of the years. These are the hours. So we are converting 25 kilowatt in year into kWh, that is kilowatt hour. So 25 into 365 days into 24 hours. So it is coming around 2,19,000 kilowatt hour per year. As per definition, capacity factor is actual production divided by theoretical production, and it is 50,000 upon 2,19,000. So it's 0.228. Therefore, we can say that turbine operates at 22.8% of its capacity. Now, it's very important to note that if this factor is less than 12, we should not use that turbine. Next problem. A miniature aero generator is designed to generate an output of 1200 watt at wind speed of 5 meter per second at 1 atmospheric pressure and temperature of 20 degrees Celsius. What will be the output if the same aerogenerator is installed on the top of the hill where the temperature is 10 degrees Celsius, pressure is 0.85 atmospheric and wind speed is 6 meter per second. So two cases are given here. One, the data is 1200 watt, 5 meter per second, 1 atmospheric pressure and temperature of 20 degrees Celsius. And another case is same aero generator at temperature of 10 degrees Celsius, pressure 0.85 atmospheric and wind speed of 6 meter per second. So in solution, for case 1, turbine power is given 1200 watt. 1 atmospheric pressure we know 1.01325 into 10 raised to 5. Density is P upon RT. This comes from the ideal gas equation, that is PV is equals to mRT. Putting the values, R is 287 for air, temperature is in Kelvin, that is 273 plus 20 degrees Celsius, that is 293 Kelvin, and the value comes around 1.2049 kilogram per meter cube. You can use calculator and can find out these values. Wind speed is given 5 meter per second. Now the power generated by turbine, we know the formula. The efficiencies of gearbox and generator is not given. Cp is also not given. We are not supposed to put that values. So P is equals to 1/2 density into area into velocity cube. Putting all the values, we'll get area is equals to 15.935 meter square. Now we will put this value in case 2 to find out the answer. For case 2, the pressure is given 0.85 atmospheric. Converting that pressure in Newton per meter square, 0.85, 1.01325 to 10 raised to 5. Density is P upon RT. Putting value of P and temperature change, that is 10 degrees Celsius now, so it is 283. So this is the value 1.0604 kilogram per meter cube. Here the speed is given 6 meter per second. So power generated by turbine is now same formula, 1/2 rho into A into U cube, but here we have to find the power generated. Therefore putting the value of A from this equation, we will put this value here. So 1/2 into density, this value, this is A from this value, and 6 cube, so it is coming around 182492 watts. So this is the required answer. I hope you understood today's numericals. We will solve some more numericals tomorrow. For any queries, you can contact me on my mail rakeshunecha@gmail.com and mobile 97633 13385. Thank you very much.